billion degrees near the nuclear black hole in the M87 galaxy. And it shows this telltale sign of a black hole sitting right at the heart of it in the shadow cast in the center of the image. And that indicates that this black hole has about 6.5 billion times as much mass as the sun. So just last week, we released a major addition to this result. So we released the first polarized image of this black hole. And these polarization images allow us to study the magnetic fields near the black hole for the first time in a resolved and really powerful way. So to produce these images requires creating an instrument with incredibly fine angular resolution. So this has about the same angular size as a donut sitting on the moon, or an atom held at arm's length. So to achieve that high resolution, we had developed a Event Horizon telescope, which is this worldwide network of telescopes that all act together as an interferometric array, where each pair of telescopes gives us one baseline that samples just one spatial frequency of the image. So by aggregating all of the information from all the different baselines, we're able to turn that into a picture of the source with this incredibly fine angular resolution. So developing this instrument took decades, and this work in particular is a collaboration involving over 300 people. But many of the key contributors to the results are actually local members of the CFA and BHI community. So we thought it'd be fun for you to hear from some of the experts on the topics involved in this work and to be able to ask questions directly to them. So today we'll first hear from Maciek Wielgus, who is going to tell us about the EHT observations and data processing. Next, we'll hear from Dom Pesce, and he'll tell us about the process of polarimetric imaging and calibration. Following that, we'll hear from Koushik Chatterjee, who's going to tell us about the GRMHD simulations, the numerical simulations that formed a big part of the interpretation of these images in the papers that were released. Following that, we'll hear from Christian Fromm, who will tell us about the ray tracing and radiative transfer that allows us to make synthetic images from these GRMHD simulations. Then we'll hear from Angelo Ricarte, and he'll tell us about the special challenges of polarized radiative transfer, and in particular, the Faraday effects that are very important in the polarized signal as it propagates through a magnetized plasma. And then finally, we'll hear from Daniel Palumbo about the physical interpretation of these results. So after these short presentations, we'll have the most important session, and that's the question and answer. So please do reserve your questions for this section at the end, and then we'll get to as many of them as possible. So with that, I'll hand things off to Maciek. So go ahead and share your screen and take it away.
Okay. Just a second. Play. Okay, is my screen visible clearly?
Yep. Yeah, looks great.
Thanks, everyone. So I'm going to talk a little bit about the observations and a little bit about the data. Not too much, because we're all anxious to hear about the theoretical results. So I will tell you, or you will learn during this next hour, really, about how did we get from this point, this beautiful image released in 2019, to this beautiful image. And you will hear about what is this fine structure that you actually see in this image. Spoiler alert, this is the orientation of the linear polarization vectors. So I will start from the beginning, somewhat from the things that we were talking about 2 years ago. What is it that we're doing? How are we doing that? And why is it rather difficult? So we want to look at the feature in the sky that is about 50 microarc seconds across, this tiny donut corresponding to this huge M87 black hole in a distance of over 50 million light years away from us. We are, however, limited by the diffraction limit. So if we want to resolve something that is 50 microarc seconds across, we need finer resolution than that. We need to go to about, say, 20 microarc seconds. If we want to use shortest wavelengths in radio that we possibly could for several technical reasons, we do need, for 1 millimeter wavelength, about 10,000 kilometers size of the telescope, which is about the size of the Earth. But we don't give up, and we do next best thing to a telescope that is actually has a dish of the size of the Earth. And this next best thing is a very long baseline interferometry. So in this technique, we take remote telescopes that work without any physical connection between them, but they perform synchronized observations of the distant astrophysical source. We record raw electric signal at the antennas, and we just take physically those petabytes of raw data to correlate them. We correlate them at facilities in Haystack, Massachusetts, and Bonn in Germany, because what we are after are the correlation coefficients between these two data streams. So when we spend time analyzing those correlation coefficients between this time series. This is the event telescope in 2018. The antenna, the array that recorded M87 data is actually a little less impressive. GLT was not a part of the array in 2017. SPT does not observe M87, which is a northern source. So we only have 5 distant locations around the globe, these 5 here. And each pair of telescopes performs a measurement. This is an interferometric measurement. Each pair constitutes a separate interferometer. So we are interested in maximizing the number of pairs of telescopes simultaneously observing the source. This is not much data, but we have another trick, if you can even call a trick the fact that the Earth is rotating. This is the aperture synthesis technique, in which, because as Earth rotates, the geometry between 2 stations and a distant source is slightly changing, we look at slightly different aspect of our source. And when I say aspect, I really mean complex Fourier coefficients of associated image of the source. There is this connection driven by the so-called Van Sittert-Zernike theory. These are our telescopes, and it turns out that if you observe with 2 detectors, each tuned to different orthogonal polarization, then between the 2 telescopes you have 4 data streams. So you have 4 correlations between 2 data streams from one telescope and 2 from the other. And it turns out that from these 4 correlations, you can actually recover a full polarization state of the source, the full Stokes vector of polarized polarization components, which is what we are after in this project. I will talk very, very quickly about what a mess is a calibration. Calibration is a real problem for VLBI, and particular for the polarization components. You can see here 2 coordinate systems, one associated with the source that is rotating with the sky. This is M87 as seen from ALMA, southern hemisphere, and the green one, which is associated to your detectors, what kind of polarization they measure. You see that they rotate one against the other. So this is a little mess because we have to do additional bookkeeping for that reason, but also it actually allows us to disentangle between behavior intrinsic to the source and certain instrumental effects, which I think that Dom will actually tell you why this is so difficult, and these components called leakage, polarimetric leakage, are a huge mess that took us 2 years about to get a good handle of. Now we can take a look at the data. And just looking at the raw data that we detect without attempting to go from Fourier plane to the image plane, you can see Fourier fractional polarization here. Don't be worried about the fact that this fractional polarization is larger than 2. This is what can happen in the Fourier domain. It's in the image domain that fractional means that it should be less than unity. What you can see already from this data without any reconstruction, you can see that this is a weakly polarized and compact source, which is actually great for the algorithm of the reconstruction. It means that M87 is not, it could be worse. It's not the worst source to try to reconstruct. Another thing that you can see here, we have 4 days of observations, and you already see that there is an evolution in the data. this source is changing on the time scale of days. The polarimetric structure is evolving. And that's my last slide. This is a slide with a bunch of happy people who have seen the polarimetric components of the image of M87 for the first time at Max Planck Institute in Germany in July 2019. And many people from whom you are hearing today are somewhere in this image. Thank you very much.
Thanks, Maciek. Okay, so next is Dom.
Okay, so hopefully you can hear me and see my screen. I'm just going to try to pick up pretty immediately where Maciek left off and talk a bit about the imaging of this polarized data set. So the polarized imaging problem is similar in many ways to the more standard unpolarized interferometric imaging problem, with the main conceptual difference being, as Maciek said, that we're aiming to solve for more information about the on-sky source structure than just the total intensity of the emission. If we think of the polarized electric field in terms of Stokes parameters, then standard imaging requires just solving for the Stokes I term, while performing polarized imaging requires solving for at least 3 of these parameters to determine the linear polarization structure. And this is more difficult not just because of the increased dimensionality, but also because the polarized flux is weak and it's easily contaminated by the instrumental imperfections that Maciek was just referencing. When the hardware receiving the 2 polarization signals at a particular telescope isn't perfect, which it never is, an issue known as polarimetric leakage can arise where some of the signal meant for one of the receivers is picked up by the other and ends up masquerading as polarization in the astronomical source. And this animation here on the right, which is the same one that Maciek showed, is illustrating how the orientation of the source relative to our polarized receivers on the telescopes changes with time, which means that this contaminating signal is also going to be time variable, and it's actually this effect that helps us to calibrate it out. And so generally, when we're doing polarimetric imaging, we have to solve not just for the polarized image structure, but also this calibration term, which can be difficult even for standard VLBI arrays, and it's only made more so by the sparseness of the EHT's coverage during the 2017 observations. So we used 5 different imaging algorithms to perform polarimetric imaging of M87, and to ensure that these algorithms were all capable of handling the difficulties presented by the EHT data, we validated them on a suite of synthetic data sets. And these synthetic data sets have varying degrees of fractional polarization, and they have diverse polarized structures. And they're shown here after blurring to the EHT's nominal resolution. Here are the, skipping over all of the technical details under the hood, here are just the results from imaging synthetic data that were generated from a particular GRMHD simulation using each of the 5 different imaging algorithms. And here's the results of applying those same algorithms to a synthetic data set generated with a more geometrical source structure. And all 5 of these algorithms were consistently able to recover the gross image structure in both Stokes I and in linear polarization, though different source structures proved different degrees of challenging. But very importantly, all of the different softwares were also able to recover the calibration terms, these leakage terms, correctly. And these plots here are showing the values of the calibration quantities that were input into each of the synthetic data sets compared against the values that were recovered from each of the softwares. And the diagonal dashed lines denote perfect agreement. We found that the typical fidelity with which these quantities, these calibration quantities, were recovered was a better than the 1% level for all algorithms. And then when applying these algorithms to the M87 data, the resulting images are shown here for each of the different algorithms, and for 2 of the days that bracket the beginning and ending of the 2017 observing run. And so there's almost a week in time that passes between the top and bottom rows of the images here. Each of these panels is showing the total intensity in the gray color scale, while the contours mark the polarized intensity. The polarization ticks show the orientation of the electric vector position angle at every location in the image, with the length of each tick indicating the magnitude of the polarized intensity, and the color of each tick indicating the fractional linear polarization. And we can see that the same general structure is found by all algorithms and on both days, with the polarized intensity being strongest in the southwestern portion of the ring, peaking at a value of about 15% of the total intensity in that region. And the orientation of the polarization ticks there being roughly azimuthal. The detailed structure in these images, though, does differ from one algorithm to the other, which is indication just of how much the different algorithmic assumptions that go into this imaging enter into the picture. So in an effort to retain only the most conservative structure that's reliably recovered by all approaches, we averaged together the images from each of the algorithms for each day. And that's now what's shown here, where the top panels are using the same sort of visualization as on the previous slide, while the bottom panels are showing the same thing, but just using a different visualization style that may be a little bit more familiar from the press coverage of this result. And we can see here that the first pair of days, April 5th and 6th, show similar polarization structure, while the last pair of days also show similar structure, but there's some noticeable evolution from the first pair to the last pair. Now in the image, it's the same evolution that Maciek pointed out in the visibilities, with the concentration of polarized flux apparently shifting around a bit in this counterclockwise direction from the first portion to the last portion of the week. And we can see this evolution a bit more clearly in this figure here on the right, which shows how the polarization changes as a function of angle around the ring, measured counterclockwise from the top. And so the top panel of these two here shows the polarized intensity, and the bottom panel shows the position angle, both as a function of azimuthal angle around the ring. And the colors here, April 5th is colored in red, and April 11th is colored in blue, these two different days bracketing the entire observing schedule. And we can see this pretty clear shift, this pronounced shift in the peak of polarization between the 2 days, while the general sweeping pattern of the azimuthal angle, or the position angle of the polarization takes in azimuth, stays quite similar in time. And so I'm just going to wrap up there. The takeaway is really that we've been able to apply 5 totally independent imaging algorithms to perform polarimetric imaging of the 2017 EHT M87 data. And we found some pretty nice consistency in the recovered polarimetric source structure across all of these algorithms. And so next we're going to have some people talk about the theoretical background and interpretation here. But I'll let Koushik take it up.
Thanks so much, Tom.
Okay. Let's see. So can everyone see my screen?
Yep, looks great.
Okay, awesome. So hello everyone, I'm Koushik, and I'll be starting off this the theory section of the image polarization papers. So to begin the theory part, we have to do the modeling of black hole accretion, right? And the way we do this is by using generativistic magnetohydrodynamic simulations, basically where we solve fluid dynamics equations, add in magnetic fields, and then solve this set of equations in the framework of general relativity. A general setup includes a spinning or a non-spinning black hole, and this black hole will be surrounded by a torus of gas, which itself is rotating, and then we'll embed some weak-ish amount of magnetic fields inside the torus just to start off the turbulence, and so that accretion begins, and then you will have accretion onto the black hole as well as, let's say, jet formation. The basic units that we use in these simulations are the gravitational radii, which is this RG term over here. So it's GM over C squared, where M is the black hole mass. Sometimes this quantity, you will also see units in terms of the black hole mass only, which is M. But in general, this is what it represents. On the right over here, I'm showing just a snapshot of a geometry simulation, a vertical cross-section of a 30 cross 30 gravitational radii box. So you have the black hole in the middle, surrounded by a torus of gas over here, represented by the density in color. So the red regions, which means high gas density, is representative of the accretion disk, and the low gas density, which is the blue region over here, that's the jet. The arrows over here indicate the velocity streamlines. So gas from the accretion disk sort of moves towards the black hole in general, or even though you see a lot of turbulence going on within the accretion disk in general. And then within the jet, you see some ordered flows going outward. And there is also an intersectional region between the jet and the disk, where you see dense material going outwards. That's the And that's the wind region where we expect a lot of emission to come from, actually. So moving on. Yes. This is just a movie, a 3D movie of a geometry simulation. So over here, you have the black hole in the middle, and you also see some spiraling gas around it. That's the accretion disk, and you also see a wobbling jet. So the geometry simulations actually give us the evolution of the gas density in the accretion disk as well as in the environment, the gas temperature, which is an important point that Christian will address later on, as well as the gas velocities. And in addition to the properties of the gas, we also get the magnetic field structure, which is quite important when it comes to, let's say, looking at the polarization. So in short, the geometry simulations give us the evolution of our accretion system, as well as the variability. Yes. So for the paper itself, we built a simulation library where we basically looked at two primary sets of GRMHD models, which were actually done with the IHAM code for the polarization paper. One set of models included different black hole spins, so going from retrograde to prograde. And the other set of models basically looked into the magnetic flux content within the disk. So either it's weak field or a disk where the magnetic fields grow to become dynamically important, which is actually quite important because one would give you a weakly power jet and the other will give you a very strong power jet, which can sort of push around the disk. So an important effect of choosing such a wide variety of black hole spins is that you will get very different kinds of jets. So on the plot over here, I'm showing on the x-axis the normalized black hole spin, and on the y-axis the normalized jet power. And you can see that there is a variety of jet powers that you can just get from changing the spin, which will actually, in effect, which will affect the disk morphology, and also sort of give you a change in the images, which we'll see later on. And this is just a small snapshot of the geometry simulation library. Yeah, and that's it, I think, from my side. So Christian will take you through the radiative transfer that we actually do to get to the images from these set of simulations. Oh, sorry. Christian.
Yep. So I'm Christian, and I will show you how we do the radiative transfer of those models. So let me share my screen and go to start the presentation. So can everyone see my screen?
Yep, looks great.
Okay, so now we do the radiative transfer, and the goal there is connecting the plasma dynamics that Koushik just showed you to the observed radiation at the end. But the first thing we need to understand is how do light propagate next to a black hole. And I show you there two figures, so please focus first on the left one. In the left one, we shoot rays from the right side of this plot, so where x is equal 10, to the black hole. And you could see them differently color-coded. So there are the blue ones, which are only slightly bending. Then you see this orange one, which bend a bit more. And you see all these black rays, and you could see that they are captured by the black hole. And there are one of those special rays, this is this red one, you could see that bends around the black hole and leaves it again. So this dark region that you see in most of these images are produced by these rays that are captured. So when you look into 3D, you could see that these red rays, they bend a lot around the black hole, and this is shown on the right side. You could see a ray which is at least 6 times bent around the black hole. And the summary of this plot is that light doesn't propagate on straight lines anymore in the vicinity of black holes. Okay, so how can we use this to make images? So here let's start with a very simple image. We have a black hole and a slit which is surrounded by a thin disk. And we look at this image at a certain inclination angle I, and we put there a photographic plate to monitor or to capture the rays. And there are two kinds of rays or two kinds of images that are produced. Let's call the first one this direct image. And this direct image, they give you the front part and the far side of the disk. So you could see this upper part over here. But due to that these rays, they propagate on curved trajectories, you could also see the bottom side of the disk. And this is shown in this lower panel over here. Okay, now we have the understanding how the rays propagate, how these images are formed. So now we apply it to the GMHD simulations. So the problem that we have with the GMHD simulation that Koushik showed you is that the temperature which we have there is from the heavy ions, but we assume that the emission is coming from the electrons. And this temperature is not evolved in the GMHD simulation. So we need to reconstruct this temperature of the ions. And what we do is we use the so-called R beta model. And I give you this equation over there. So it depends on the temperature of the protons, which are evolved by the GMHD, and on the plasma beta. That's the gas pressure divided by the magnetic pressure. And we have a parameter, which is called R high, which we can scale between 1 and large number to get these temperature ratios. And I show you on the right side how this affects the temperature if you change this R high. So the left part of this panel is the plasma beta. You could see a low plasma beta in the jet funnel, where these are the top and the southern bluish color. And you have a high plasma beta in the disk region. So now we apply this equation for different R high values. And this you can see on the right. So at 1, you could see it's yellowish and red in the jet. And then when you pump up this R high value, you could see that the disk becomes cooler and cooler. So it becomes bluer and bluer. And the jet becomes brighter. So the summary here is that when we increase the R high, we go from a disk-dominated temperature model to a jet-dominated one. Okay, now we apply this to all these models that Koushik showed you in the library, and we get the images, and these images we Fourier transform and compare it to the observation. And on the top here, you could see two of the best scoring models. So the left one is the sane one with a weak magnetic field, as Koushik explained you, then the counter-rotating one, and the right one is a mad one, strong magnetic field with a lower R high value. In the middle, you could see the image of the M87 observations, the unpolarized one, so the one that we published last year. So when you compare the ray traced images left and right to the middle one, you could see that they do not really correspond to each other. But what you have to take into account is the way how these images are observed. And if you take into account the observations, so the sparse sampling of the UV plane that Maciek showed you, and these different image reconstruction methods that Dom showed you, you get the images on the bottom panel. And you could see that they do a quite nice job to match the observed signatures. So all what I showed you was the total intensity, and now Angelo will guide you through the polarized radiative transfer.
Thanks, Christian. All right, so when it comes to polarization, now the radiative transfer has become more complicated and dependent on more of the physical parameters of the disk, but this is good because we would like to extract parameters such as density, temperature, and magnetic field. What we observe in the millimeter is synchrotron radiation, and intrinsically, this has a large linear polarization fraction in the realm of 70%. When this is emitted, the light is oriented perpendicular to the local magnetic field along the line of sight. And you can infer that by envisioning electrons spiraling around magnetic field lines as shown in this image to the right here. Then after this polarization is emitted, it gets further modified as it travels through the intervening plasma by Faraday effects. And these are sensitive to temperature, density, and magnetic field, making this process potentially complicated, but also encoding a lot of physical information in there. So because there's this relationship between the emitted polarization of light and the geometry of the magnetic field, we can gain an intuition into how the magnetic field gets mapped onto the polarization ticks. as in this, here we go, this movie made by Crazy Bridge Studios that came out of our group. This is mainly an effort led by Nick Conroy, Daniel Palumbo, and myself. And here we start out with a black hole with an accretion disk. We're viewing M87 face on. And in the case of weak magnetic fields, they get sheared along with the rotational motion of gas in the disk into this toroidal configuration. And so when light gets emitted by magnetic fields in this kind of geometry, the circular magnetic fields get turned into apparently radial polarization ticks by doing that rotation by 90 degrees. On the other hand, with very strong magnetic fields, we found that if the magnetic field strength increases, the poloidal component of the B field increases. And in the extreme case, the magnetic fields will buckle against the toroidal configuration and become more radial, such that you would get a polarization configuration that looks more like that. And then, of course, nature will probably fall between these two extremes. If you have a magnetic field with both radial and toroidal components, you will end up with something with this kind of spirally pattern. And this is starting to now roughly resemble the EHT's observations with both a radial and toroidal component to the magnetic field. However, I've skipped over important effects, including Doppler beaming, the effect of lensing, and importantly, Faraday rotation, which is going to rotate these polarization ticks and cause depolarization as well. So these Faraday effects that I mentioned before are, again, Faraday rotation, which is going to turn that polarization plane. And then there's also Faraday conversion, which exchanges linear and circular polarization modes. In the models of interest for M87, we think that Faraday rotation is really important. Some of these can be very, we say Faraday rotation thick, the same way we say optically thick. While we think that Faraday conversion is less important, but can be important for generating most of the circular polarization in principle. Now, emission is most directly sensitive to the hot electrons, but these Faraday effects are sensitive to the cold electrons. This is good because this starts to break model degeneracies and cause us to be sensitive to an otherwise invisible population. And Faraday rotation is important for depolarizing these images. In this table on the bottom here, I've written different values of the linear polarization from ALMA-only data as well as the EHT resolved data. They're in the realm of 1 to 10%, which is much less than the 70% that I said that synchrotron was intrinsically. If you look on these figures to the right here, on the top is one model image for M87, and on the bottom is the same thing if you turn off Faraday rotation. Here, the colors are encoding the linear polarization in a given pixel, with red being the highest. And so you can see that adding the Faraday rotation is really important for depolarizing. What's happening is that this Faraday rotation is inside of the emitting plasma, and ticks are rotating around enough to scramble each other if one averages over the beam. All right, and I'll end there and pass on to Daniel.
Great, can you guys hear me?
Yep.
Awesome, all right, let me share my screen. Hopefully this works. What is this, Control F5? All right, hopefully you can see this.
Looks great.
Great. My name is Daniel Palumbo. I am here to give you a sort of big picture of the analysis that we performed in paper 8 to pin down some of the properties of the accretion flow of M87. The idea here is that we have this beautiful library of GRMHD simulations that you heard about from Koushik, where we sample truly a massive number of both sort of random instantiations of the accretion flow, but also a very broad parameter space of spin and magnetization and the electron distribution function by way of these R low and R high parameters. And the details here aren't super important for this audience. I think mostly what I'd like to focus on here is that there's many snapshots here with a variety of sort of structures that your eye might be drawn to. You know, they have these bright swirly arms, they're very morphologically complex. But at the EHT resolution, they're blurry, and you can reduce them to a few numbers that are easier to think about and easier to compare for the purposes of the sort of physical inferences that we would like to draw. So at the end of the day, it's actually a rather simple pipeline for analyzing why we think M87 has certain properties, which I will tell you about. So we receive this beautiful distribution of images of M87 from our data people and the people who actually do reconstructions and model fits, as we heard about from Maciek and Dom. And we can pose a few questions, like how polarized is the image at our resolution or when it's unresolved, so essentially integrating over the image, or how rotationally symmetric is the polarized image? What does this spiral look like in a quantitative sense? All of these questions are affected by the details of the Faraday effects, both internal and external to the flow. And they're also tied to the magnetization of the flow. Particularly, this last question is getting exactly at the geometry of the magnetic field itself, provided that it survives all of the Faraday effects between us and the interior. And so we can pose these in a quantitative way and see how they shake out, where the EHT images lie in the parameter space, or really the sort of post-processing parameter space of the GRMHD library. So to begin with, we look at this resolved linear polarization. So the EHT has a resolution of roughly 20 microarc seconds. We can take our GRMHD library and blur to this resolution, and we get some measure of the linear polarization we would expect to see if the EHT were to actually look at one of these GRMHD simulations with our array of dishes. And what we find is that the reconstructions of the actual data fall in a fairly tight band that is suggestive of very strong Faraday effect. So rotation depths of greater than 10, as you can see on this right plot, as exactly as Angelo was telling you. And this left plot is already decently discriminating in the sense that it cuts out this big chunk of sanes on the low end. But I want you to keep this middle plot in mind, where it's going to come back to haunt us in a couple slides. The second question that I posed earlier of what does the net polarization look like, this is related to the first question in that it's also very sensitive to Faraday effects, which are depolarizing our image below the beam scale of the EHT. It's also sensitive to morphological cancellations. If you had a perfectly rotationally symmetric image of polarization, then you would end up with zero net linear polarization because it would just cancel out. And so we compose this for linear and circular polarization, and we find a rather small net polarization in both cases. Finally, we can analyze the pattern of this spiral. So this is posed in terms of these PWP coefficients, particularly the beta 2. This will look very familiar to you if you're familiar with observational cosmology. This is completely identical to E and B modes, just defined in terms of averages over the image plane. And this is essentially a complex number which tells you whether you look more radial or more sort of circular or like right or left-handed spirals. And all of these images with remarkable consistency across reconstruction methods and across posteriors of the fits, all of these end up with something between a beta 2 of -1, so something circular, and something that's a right-handed spiral, so -I. So in the complex plane, this is all bottom left quadrant. Now, the amplitude of this coefficient is very similar in its distribution to the fractional linear polarization on a resolved scale. And this is not an accident. It's the way this coefficient is built. So we're not getting too much new information here. But the phase of this coefficient is telling us what does the spiral look like. When we look at this image, it looks like a modest right-handed spiral. It turns out that is highly discriminating, particularly with respect to retrograde sanes. These are the dark orange histogram in the bottom right. These are very good at mimicking M87 in many other respects, but in this one, this is highly constraining. And so finally, we can put all of these together, and the details of how you put these together determine a little bit of the output. This is one of the tests that we did in this paper is you can pose a few different reasonable ways to put together these constraints. You can demand that certain sets of the parameters simultaneously fit all of our observations with one of their snapshots, or you can assign relative likelihoods by taking a fraction of the images that fit and multiplying them together. And these will change the relative preference for things like R low, R high, and even spin. But no matter how you cut it or slice it or score it, MADs are favored very strongly. And so all of these tests are done purely with polarized information on their own terms. But when you take the jet power constraint from paper 5, so just demanding that the GRMHD simulations produce the jet power that's expected from other observations, that cuts out not only everything that's spin 0, but all of the sanes. So the combination of the polarimetric data and this jet power constraint is enough to tell you that M87 sure darn near looks like a MAD, at least given our knowledge of the GRMHD. And so then we can put this through our post-processing and get our constraints on the accretion rate and the jet power. And the jet power distribution is still pretty flat over these couple orders of magnitude, but the accretion rate is slightly better constrained now. So the paper 8 goes on to tell you all kinds of exciting things that we can do at higher frequencies and with a bigger array. But for now, this is where we leave off. And I think now I'm handing off to Alex Raymond.
Yeah, so apologies, I forgot to introduce Alex at the beginning, but Alex is going to tell us about the next generation of event horizon telescope and prospects for even sharper polarimetric images.
Yes, can you see my screen okay?
Looks great, yeah.
So over the past couple of years, we've been thinking about what we might like to do next in terms of the instrument, the HT instrument. And this project that we've been working on is an expansion to the EHT, the next generation EHT. And the NGHT has 4 main features. It will have new stations in addition to what are presently in the HT shown in blue. A set of candidate stations are shown in this map in red. So roughly doubling the number of stations, doubling the bandwidth to improve the sensitivity of the instrument. We're planning for simultaneous 230 gigahertz and 345 gigahertz observing, and also flexible observing. At present, the HT observes in a campaign style a few days out of the year, and we'd like to have more routine, flexible observing to capture interesting phenomena on our sources. And so what this means in terms of polarimetry, like the result that's been discussed today, is that we have much better coverage on our source. So in 2017, the spatial frequencies that we're sampling are shown here on the left, again with this fractional polarization in the Fourier domain shown in color scale. And in our current array, we've grown a few stations, and so the current array 2021 has a bit better coverage, but the NGHT, we are preparing for significantly greater coverage even beyond that, shown in the right panel. And this allows us to capture interesting features like these pockets of highly polarized flux. And so what this means in terms of imaging reconstructions, and this is based on a simulated model that was produced by Andrew Shale, who was a graduate student here with Ramesh Narayan. This model, if we sample it with 2017 coverage and perform a polarimetric reconstruction, we see something similar to the current results where we're looking at horizon scale polarimetry, and that improves a bit with the current array, the 3 additional stations I mentioned, where we start to get a little bit of the jet flux captured. But with the NGHT coverage and sensitivity, we expect to have polarimetric coverage out on the jet to several shadow diameters. And so this is something we're really excited about in the future of our instrument. I think that's all I wanted to share.
Great, thanks, Alex. So I guess I'll ask for questions now. I think it'd be best if people raise their hand just so we can keep track of things, or feel free to drop them in the chat. And panelists, just be ready. So I see Alex has a question. Go for it.
Maybe I missed this, but is there a circular polarization image, or is it just consistent with 0?
Let's see. Dom, do you want to take that one?
Sure, yeah. So the data we've collected certainly contain circular polarization information that hasn't been released in this first polarimetric imaging paper. So the linear polarization image is the only one we've released, and there are constraints on the very large scale integrated circular polarization from ALMA only data on just many orders of magnitude larger spatial scales, and it's very small, under 1% and consistent with 0. But we haven't released an attempt at a circular polarimetric image in this round of papers.
Great, Shahar?
Yeah, I wanted to ask, so you talked about two different configurations of the magnetic field, the toroidal and poloidal, but what about magnetic fields which are like vertical and thread the equatorial plane? I mean, what's the signature of that?
Yeah, Daniel or Koushik?
Sure. So we use poloidal essentially to refer to combinations of radial and vertical. They can MADs can have pretty strong combinations of either. You can actually end up with decently strong radial fields even in some stains, but the manifestation of these is shown to a certain degree in some of the pedagogical figures in paper 8. In general, if you look face on enough or at slight inclinations with a vertical field, you can end up with spirals, even though the vertical field is still, it's essentially pointing directly at you, just because you're getting sort of lensing and aberration effects. Basically, it's complicated, and the peaks in polarized intensity don't always line up where you might intuitively expect. And so thankfully, this is all sort of self-consistently built into to our metrics, because we are so far downstream of the physics. But toy models help elucidate this, which is partially explained in the paper.
Did you want to comment on it at all, Koushik or Christian?
No, that's seemed pretty comprehensive.
Okay. Yeah, any other questions? Andy.
Yeah, if you look at other black holes in the sky where you can't resolve the image, I guess, have there been measurements of the averaged polarization, and how does this, if so, how do these compare to those? And is there any general correlation between averaged net polarization and spin?
Yeah, I'm wondering who could present.
Is there any?
Angelo, do you want to comment on that, or?
I'm aware of some work on this, such as the Mojave survey. There do exist many unresolved polarization measurements. In terms of to what extent they correlate with spin, I would ask how would you get the spin? I'm not aware of.
Well, there's dozens of black holes where they think they have the spin, and maybe they have.
I'm thinking of the polarization. Not CAJ, I guess. But anyone else want to jump in?
Yeah, Andy, so you're thinking of X-ray binaries, right?
Anything.
Yeah, so I mean, so Angelo's right. I mean, it's and Matt Lister, the PI of the Mojave survey, is on the call, I think. So feel free to chime in. I think it'd be great if this was just an informal discussion among BHI community members. But yeah, so they regularly do these monitoring campaigns on the supermassive black holes. The linear polarizations are typically quite low when they're unresolved. Often less than 10%. 10% is considered a pretty highly polarized source for us. In terms of connecting that to spin, I think it's quite difficult, because the spin measurements are still very speculative. We don't have some concrete, we're staring at the spin of the black hole like we do with the mass of M87 yet. So the other thing is the linear polarization tends to be extremely variable. So both in angle and in magnitude, right? As a function of time, it'll be burbling all over the place. So if anything, you'd probably be more likely to get at the spin through the variability, as opposed to measuring a particular angle or a particular magnitude. But yeah, I'd say, or Matt, go for it. Yeah.
Yeah, the other thing you have to worry about is Faraday effects that you can't, essentially, because the LBI we do is centimeter wavelength. So if you go to high frequency like EHT, there's less Faraday effects and there's less blending effects. So once you go out to higher redshifts, which were the polarized, highly polarized AGN targets, you get blending of the polarization features and you get Faraday rotation. So really the only regions you can study are downstream of the black hole at the moment, until we get EHT and enough sensitivity that we can start to push out to past M87. And that's where things get interesting.
Another thing to keep in mind is, the way we make constraints on models, we heard about a lot of these different constraints and then they're aggregated. So one particular constraint doesn't necessarily come from a specific measurement. If we say that MADs are favored or something, that might require a set of measurements. So for instance, even with the full polarized image of M87, we still can't constrain the spin. By insisting that our simulations have as much power in the jet as is observed for M87, we can say that the black hole has to be spinning. And we know the direction from the side that it's bright on, but beyond that, we don't have tight constraints on the spin magnitude. So I think even with resolved image, it's still hard to make conclusive statements about the spin. Any other questions or comments? I see one. Oh, that was it.
Maybe one comment to this. You also have to, let's say, consider the particle distribution. So this far, I think we used a thermal distribution for the emitting particles. But when you go along with this JetMat lister and the Mojave people see, we need to consider also non-thermal distributions, and more important, where they change from the thermal to the non-thermal one, because they have different rotativities, and this will lead to different Faraday rotation effects.
Yeah, thanks, Christian.
I wonder if I could ask a naive question.
Go for it.
Relating to. Go for it. So is my understanding that the photon ring, well, the ring you see is, a lot of that is photons which are making one or more orbits. So how do you preserve the polarization information and backtrack to the magnetic field that produced those photons if they've gone around one or two times?
That's a great question. As promised at the beginning, I'm going to kick that to Mena if you're up for it. You want to comment on? Yeah.
Well, I think right now most of the flux is in the direct image only. So we're looking at, mostly just things that didn't orbit the black hole that came at us directly. But if you're looking at sub-image polarization, it will be additionally rotated relative to the direct image. And so you could actually think about looking for the lens polarization images by looking for regions of relative depolarization. But I think that we don't have resolution available to see this up things right now. I don't know. Everyone else, feel free to comment also. Yeah.
Yeah. Well, I think, like everything in polarization, it's a very rich problem. And as you dig deeper, there's a lot of interesting structure in the photon ring, which, Mena led a paper on this. But we don't think that structure is what's dominating the image that we see right now. So definitely a target for NGHT science. Yeah. Shep.
I was just going to make the comment that this is a good case for space VLBI, because of course, if you launch something into space, you get much better angular resolution, and then you can see preferentially the inner rings. And that's what Mena's work, I think, is showing. So more impetus to leave the planet.
Yep. Any other questions or comments?
Congratulations.
Yeah, congratulations.
Yeah, well, thank you. And thanks all for joining this evening, and especially the panelists for preparing their presentations. But, really, this is the joy of being at the BHI, is that we hope that these results will prompt new discussions, new collaborations, and new ideas. So don't be shy about reaching out, and we look forward to talking more about these results with you in the coming months. So thanks, everyone, and have a great night.